Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing structure of selective anionic radicals. The contents of this module are hybridization and geometry from molecular formula, prediction of shape of molecules and ions, structure of nitrate ion, structure of carbonate ion, structure of sulfate ion, structure of anions with lone pair on central atom, that is structure of nitrite and sulfite ions. First of all, we are discussing hybridization and geometry from molecular formula. It should be noted that the molecular formula can be used to calculate the hybridization. From the hybridization, we can arrive at geometry. From the geometry of a molecule, you can ignore the lone pair if any present on the central atom to get the shape. So, ultimately, from the molecular formula, you can arrive up to the shape of the molecule or symbol ions. We are now discussing how to get hybridization and geometry from molecular formula. First of all, hybridization and geometry from molecular formula. For this, we are having some previous knowledge with us. We have to recall some concept, and it is possible to calculate the hybridization of the central atom in simple molecules and ions from the molecular formula. From the hybridization, we can arrive at geometry of molecules and ions. The equation used to determine hybridization from molecular formula is here. That is, hybridization is equal to half into V plus M minus C plus A. In this expression, it should be noted that V represents number of valence electrons around the central atom. M represents number of monovalent atoms around the central atom. For example, hydrogen and halogen atoms are monovalent, but oxygen is a divalent element. And the next term C represents cationic charge and A represents anionic charge. So, by using the expression, it is possible to calculate hybridization from molecular formula. Now, we can illustrate the determination of hybridization from molecular formula by taking some examples. First of all, we are taking nitrate ion, that is nothing but NO3 minus ion. Here, the central atom nitrogen is having 5 valence electrons and there is no monovalent atoms. This is because oxygen atoms are divalent atoms. So, in order to substitute in the expression for hybridization, you have to use M is equal to 0. Thus, since it is an anionic radical, the value of A is equal to 1. That is, we have to use these values. V is equal to 5, that is number of valence electrons around the central atom nitrogen is 5. Number of monovalent atom M is equal to 0. Cationic charge is equal to 0 and A is equal to 1, since it is associated with a 1 unit negative charge. So, we have to put all these values in the expression for hybridization. That is, hybridization is equal to half into V plus M minus C plus A. So, on substitution, we will get half into 5 plus 0 minus 0 plus 1 and the result will be equal to 3. The number 3 represents the fact that 3 orbitals are take part in hybridization. For simple molecules and ions, we know the 3 orbital hybridization is nothing but sp2 hybridization. That is, we determined the hybridization of NO3 minus ion as sp2. Moreover, we can clearly speak like this: the central atom nitrogen in nitrate ion depict a hybridization of sp2. Now, we are taking another example, that is nothing but nitrite ion. Nitrate ion is NO3 minus and now we are taking nitrite ion as the example. Nitrogen atom is again the central atom and you know that nitrogen is associated with the 5 valence electrons, and since oxygen atoms are the atoms surrounding the nitrogen and they are divalent, here we can say that in this nitrite ion there will be no monovalent atoms. It is having an anionic charge of -1. Thus, we can conclude that V is equal to 5, that is number of valence electron is equal to 5, monovalent atoms equal to 0, cationic charge is equal to 0 and anionic charge is equal to 1. We know hybridization H is equal to half into V plus M minus C plus A. On substituting the values, we will get 3 as the value of hybridization. 3 represents 3 orbitals that take part in hybridization, and absolutely we can make it clear that the hybridization is sp2. So, NO2 minus ion shows sp2 hybridization. Similar to NO3 minus, NO2 minus also has a hybridization of sp2. Can you say why both ions have same hybridization? This point is very remarkable. NO3 minus is nitrate ion. Here in this slide we discussed about nitrite ion, and we calculated the fact that both exhibit same hybridization sp2. Now, what is the reason? Even though the molecular formula is different, why these two species exhibit same sp2 hybridization? The answer is this: they differ. These two species differ only in the number of oxygen atoms. In the expression for hydrogen hybridization, the number of divalent atoms need not be considered. Oxygen is a divalent element. So, change in number of oxygen atoms will not alter hybridization. We can have several other examples. SO4 2 minus is sulfate ion, SO3 2 minus is sulfite ion. They differ by one oxygen atom. Since oxygen is a divalent element, it should be noted that both the sulfate and the sulfate ions have the same hybridization. Now, we are discussing another example, another anion, that is nothing but carbonate ion. Carbonate ion is having the molecular formula CO3 2 minus. You have to keep the fact that this module is aiming the discussion of structure and shape of some selective anionic radicals. That is why we are taking selective anions as the representative example. So, in this example, we are now focusing CO3 2 minus ion, carbonate ion. Here the central atom is carbon. You know, carbon is a tetravalent element. That means the central atom carbon has 4 valence electrons around it, and in carbonate radical, in CO3 2 minus ion, there will be no monovalent elements because the oxygen atom is a divalent atom. So, there will be no monovalent atom. It is an anionic species with a charge of -2. So, we can conclude that V is equal to 4, that is number of valence electron is equal to 4, number of monovalent atom is equal to 0, cationic charge is equal to 0, and anionic charge is equal to 2. And we have to substitute all these values in the expression for hybridization, that is hybridization is equal to half into V plus A minus E plus A, and on substituting these values, we will get the result half into 4 plus 0 minus 0 plus 2, that is equal to 3, the number is 3. The number 3 indicates that 3 orbitals are take part in hybridization, and absolutely it is clear that the hybridization is nothing but sp2 hybridization. So, the carbonate anion exhibit sp2 hybridization with respect to the central atom carbon. Now, we can take another anion, that is sulfate anion, SO4 2 minus, as another example. In this case, SO4 2 minus ion, in the case of SO4 2 minus ion, sulfur atom is the central atom, and sulfur belongs to oxygen family, and sulfur has valence electrons number equal to 6, or sulfur is associated with the 6 valence electrons, and here all other atoms are oxygen, and hence SO4 2 minus has no monovalent atoms. SO4 2 minus is an anionic species having a charge of -2. So, we can conclude that V is equal to 6, number of valence electron is equal to 6, monovalent atoms equal to 0, cationic charge is equal to 0, and anionic charge is A is equal to 2. What substituting in this expression, we will get the hybridization equal to 4. That means 4 orbitals are take part in hybridization. For simple molecules and ions, the 4 orbital hybridization is nothing but sp3 hybridization. Thus, we can arrive at the conclusion that the sulfate anion shows a hybridization of sp3. We can now take another example, that is nothing but sulfite ion. Sulfite ion is SO3 2 minus ion. SO4 2 minus is sulfate and SO3 2 minus is sulfite. I just mentioned you the fact that the number of oxygen atom will not alter the hybridization provided the central atom and the total charge being the same. Now we can check it out. Sulfur is the central atom with the 6 valence electron and no monovalent atoms are here. It is an anionic charge, this species is having an anionic charge of -2, and thus we can say that V is equal to 6, M is equal to 0, cationic charge is equal to 0, and A is equal to 2. On substituting in the expression, we will get hybridization is equal to 4, that is the hybridization is sp3. It is very well clear that SO4 2- that is sulfate anion and SO3 2- that is sulfate anion both have same hybridization, that is nothing but sp3 hybridization. Now we are discussing the connection between hybridization and geometry. The type of hybridization determines the geometry and bond angle of a molecule or ion. From this chart, it is clear that hybridization fixes the geometry, or hybridization determines the geometry of the molecule. As an instant, it is very common factor, it is very important thing, and it is a very simple matter of interest. And sp hybridization leads to linear geometry, sp2 hybridization leads to trigonal planar geometry, sp3 leads to tetrahedral geometry, sp3d hybridization leads to trigonal bipyramidal geometry, and finally sp3d2 hybridization leads to octahedral geometry. Thus we can ultimately speak the fact that hybridization determines geometry of a molecule. Now we are discussing prediction of shape of molecules and ions. How to predict the shape of molecules and ions? If you are knowing the hybridization, you can arrive at the geometry. From the geometry of the species, you can ignore the lone pair if any present to get the shape of the molecule. We are discussing such important area, that is nothing but prediction of shape of molecules and ions. It is possible to predict the shape of simple molecules and ions by using the concepts of VSEPR theory, that is valence shell electron pair repulsion theory and hybridization. The different steps to arrive at the shape of molecules and ions are shown here. In the first step, you have to determine the hybridization of the molecule or ion from the molecular formula. In the second step, you can arrive at the geometry of the molecule from the hybridization, because hybridization determines geometry of the molecule. In the third step, you can identify the position of the lone pair, if any, on the central atom in the geometry by using VSEPR principles. So, if there is a lone pair on the central atom, you have to fix the position of the lone pair around the central atom on the basis of the principles of VSEPR theory. Now, in the fourth step, you can ignore the lone pair, if any, present on the central atom to get the shape. And this is most important point, that is step 5. If there is no lone pair on the central atom, the geometry as such is taken as a shape. That is, geometry and shape will be same if there is no lone pair of electrons on the central atom. Thus, it is possible to arrive at the shape of molecule by simply starting from the molecular formula. From the molecular formula, you have to determine the hybridization. From hybridization, you have to determine the geometry. From geometry, you can arrive at the shape by ignoring the lone pair, if any present. If there is no lone pair, the geometry will be same as a shape. Now we can illustrate these prediction of a shape by taking some simple examples. For these examples also, we are taking some anions as representative, because this module is selectively intended to discuss the shape of some selective anions. Example number 1, nitrate ion, NO3- ion. The first step is the determination of hybridization. Hybridization is equal to V plus A minus A plus A divided by 2. On substituting the values of V, M, C and A, we will get the hybridization of the nitrate ion as sp2 hybridization. That is, in NO2- ion, the central atom nitrogen shows sp2 hybridization. In the second step, we are going to determine the geometry. Since the hybridization is sp2, the species is associated with the trigonal planar geometry. But in nitrogen, there will be a lone pair of electron. So, the exact geometry is trigonal planar with one lone pair. This is the geometry of NO2- ion. Here you can see the position of lone pair also. One corner of the triangle is occupied by the lone pair. Now, In step 3, you are going to identify the position of the lone pair. The position of the lone pair is one corner of the triangle. And in the fourth step, you are going to ignore the lone pair, since there is one lone pair on the central atom nitrogen to get the shape. Thus, the shape is bent as shown here. The left side represents nitrite ion with trigonal planar geometry having one position occupied by lone pair. You are removing that lone pair to get the shape. The shape is bend shape or V shape. Now we are taking another example, that is nothing but nitrate ion, NO3 minus ion. We already learned the fact that NO2 minus and NO3 minus both exhibit the same hybridization, that is nothing but sp2 hybridization. So, determination of hybridization is the first step. We already made it, and hybridization is equal to 3. That is 3 orbitals take part in hybridization. That means the exact hybridization is sp2. So, in nitrate ion, the central atom nitrogen exhibit sp2 hybridization. And we can determine the geometry in the second step. The geometry is trigonal planar and there is no lone pair of electron on the central atom nitrogen. This is the geometry of nitrate ion, that is NO3 minus. Now, in the next step, the position of the lone pair to be identified. Since there is no lone pair on the nitrogen atom, we don't worry about the position of the lone pair. And the last step is ignorance of lone pair to get the shape. We know that in this molecule there is no lone pair and hence geometry is the same as shape. So, geometry as well as shape of nitrate ion are similar. They are nothing but trigonal planar. This is the trigonal planar shape of nitrate ion, NO3 minus ion. Now we are discussing another example, that is nothing but a sulfate or SO4 minus ion. Here we are going to determine the hybridization in the first step. As you know, the hybridization is equal to 4, that is sp3 hybridization shown by central atom sulfur. In the second step, you are going to determine the geometry. The geometry of the molecule is a tetrahedral because your hybridization is sp3. This is the geometry of sulfate ion. You cannot see any lone pair around the central atom. So, you don't bother about the position of the lone pair since there is no lone pair around the central atom. And the fourth step is you have to ignore the lone pair. If any, since there is no lone pair, you can simply say that geometry is the same as the shape of both are tetrahedral, and this is the tetrahedral shape or geometry of sulfate ion SO4 minus. Now, we are taking another example, that is nothing but sulfite ion SO3 2 minus ion. SO4 2 minus and SO3 2 minus both are associated with the same hybridization, that is nothing but sp3. So, determination of hybridization gives you the result that the hybridization of SO3 2 minus is sp3. In the next step, we are going to determine the geometry. The geometry of the molecule is tetrahedral, but there occur the presence of a lone pair of electron on the central atom sulfur. So, this is the tetrahedral geometry with one position occupied by lone pair. This is the geometry of the sulfite ion, that is SO3 2 minus ion. Now, in the third step, you are going to fix the position of the lone pair according to VSEPR theory principles. So, the lone pair position is one corner of the tetrahedron. The four corners of the tetrahedron are identical. So, the position of the lone pair is at any position at any corner of the tetrahedron. So, in the last step, we are going to arrive at the shape by ignoring the lone pair. You know there is one lone pair of electron around the central atom sulfur in SO3 2 minus. Now, you are going to remove that lone pair to get the shape, and the shape is trigonal pyramidal. So, SO3 2 minus ion or sulfite ion depicts trigonal pyramidal shape or simply the pyramidal shape. Now, we are taking carbonate ion or CO3 2 minus ion as a representative example. Here, we are going to determine the hybridization first. Central atom being the carbon atom, 4 valence electrons are present, no monovalent atom, cationic charge is 0, anionic charge is 2. On simple substitution, you can arrive at the hybridization as sp2. So, the carbonate radical, carbonate anion shows sp2 hybridization with respect to central atom carbon. In the second step, you can determine the geometry of the carbonate ion from the hybridization. The hybridization is sp2, so you can say that the geometry of the carbonate radical is trigonal planar. This is the geometry of the carbonate radical. Here you cannot see any lone pair of electron on the central atom carbon. So you need not consider the position of the lone pair since there is no lone pair of electron around the central atom carbon. So in the last step, you are going to ignore the lone pair. Since there is no lone pair, you can arrive at the conclusion that geometry is the same as the shape. Both are trigonal planar. That is, carbonate anion shows trigonal planar shape as well as trigonal planar geometry. Some structures of selective anions. First of all, structure of nitrate ion. In the nitrate ion NO3 minus, the central atom nitrogen shows sp2 hybridization. That is, the hybridization scheme of the central atom nitrogen is sp2. This we can illustrate by looking onto the electronic arrangement. This is the ground state nitrogen configuration, that is nothing but 2s2 2p3. The electronic configuration of nitrogen is 1s2 2s2 2p3. Only valence electrons will undergo chemical bond formation as well as hybridization. So you have to consider the outer shell configuration, that is nothing but 2s2 2p3. The 2s2 2p3 arrangement is shown here, and it should be noted that in the structure of NO3 minus ion, the central atom nitrogen assumes a formal positive charge of +1. So in the next step, I am representing the arrangement of nitrogen plus. The nitrogen plus lacks 1 electron when compared with the nitrogen. So this is the arrangement of nitrogen plus, and in this nitrogen plus, 1 s orbital and 2 p orbital undergo hybridization, that is nothing but sp2 hybridization. At the same time, you can see that 1 p orbital will not take part in hybridization. So 1 hybridized p orbital is present in the nitrogen plus. So we have to consider how NO3 minus ion is produced. In looking onto the structure, you can see the presence of 4 bonds, out of which this bond is sigma bond, but this bond is a pi bond. This is sigma bond, this is also a sigma bond. So in the structure of NO3 minus ion, you can see the presence of 3 sigma bond and 1 pi bond. The 3 sigma bonds are produced from 3 half-filled sp2 hybrid orbitals. At the same time, the pi bond is produced by the lateral overlap of unhybridized p orbital with a p orbital from the oxygen atom. So this leads to generation of NO3 minus ion. Now, based on the hybridization and VSEPR theory, the geometry can be predicted as trigonal planar. Once the hybridization is predicted, you can arrive at the geometry. The geometry of nitrate ion NO3 minus is trigonal planar. So this is the trigonal planar arrangement. It should be noted that there will be no electron pair around the central atom nitrogen in NO3 minus, and hence there is no lone pair, and the structure and the geometry of nitrate ion will be the same. That is, the structure and the geometry are trigonal planar. That is, NO3 minus ion shows trigonal planar arrangement. Moreover, this part is aimed to discuss the structure. It should be noted that nitrate ion is a species which show the phenomenon of resonance. What do you mean by the term resonance? Resonance means this is a phenomena in which the structure of a single molecule cannot be represented by one structure, but more than one structure is required. The individual structures are contributing structures or canonical structures, and the actual molecule is a resonance hybrid of all these structures. These are the possible resonating structures of nitrate ion NO3 minus ion. Now we are discussing the structure of another species, another anionic species, that is carbonate ion. Structure of carbonate ion. In the carbonate ion, that is CO3 2 minus, the central atom carbon depict sp2 hybridization. This is the electronic arrangement that lead to sp2 hybridization in carbonate radical. This is the ground state arrangement of the carbon atom. Carbon atom has a configuration, outer shell configuration of 2s to 2p2. Here, one electron from 2s orbital is excited to the vacant 2p orbital to get the excited electronic arrangement 2s1 2p3. And among these, one 2s orbital and 3 2p orbital, one 2s orbital and 2 2p orbitals undergo hybridization, lead to sp2 hybridization, and there is one unhybridized p orbital is also present in the carbon atom. So, these hybrid orbitals, sp2 hybrid orbitals, 3 sp2 hybrid orbitals lead to the formation of 3 sigma bond, and one unhybridized p orbital lead to the formation of 1 pi bond. So, in carbonate radical, you can see the presence of a total of 4 bonds, out of which 3 are sigma bonds and 1 is a pi bond. Based on the hybridization and VSEPR theory, the geometry can be predicted as trigonal planar. I already mentioned you that in the carbonate radical, there are a total of 4 bonds, out of which 3 are sigma bonds, which are formed from 3 sp2 hybrid orbital, and 1 is a pi bond, which is produced from unhybridized p orbital present on the carbon. Now, there is no lone pair of electron on the central atom carbon in carbonate ion. That means the structure and the geometry of carbonate ion are same. The structure and the geometry are trigonal planar. This is the trigonal planar geometry or structure of carbonate ion. Again, as in the case of the nitrate ion, carbonate ion CO3 2 minus also shows resonance structure. This is the resonance structures of carbonate ion. You can see 3 resonate structures. These 3 resonating structures contribute towards the total structure. The actual structure can be considered as a resonance hybrid of these 3 resonating structures. Now, we are discussing structure of sulfate ion. Sulfate ion comprised of central atom sulfur. The sulfate ion central atom sulfur shows sp3 hybridization, which can be depicted like this. We know central atom sulfur in the ground state has an electronic arrangement of 3s2, 3p4, 3p4 can be represented like this: 3p1, 3p2, 3p3, 3p4, 3s2, 3p4, and there will be no electrons in the 3d orbital. There are 5 3d orbitals. That is, this is the ground state electronic arrangement of sulfur in sulfate ion, SO4 2 minus ion. Now, sulfur undergo excitation. For this, electrons jumped from 3p to 3d. At the same time, 3s electron also promoted to 3d. So that you are getting a new arrangement: 3s1, 3p3, 3p1, 3p2, 3p3, and at last there are 2 electrons in 3d subshell, that is 3d1 and 3d2. This is the excited state arrangement of 3s. This is arrangement in 3p. This is arrangement in 3d. And among these half-filled orbitals, 1s orbital and 3p orbital undergo hybridization. That is nothing but sp3 hybridization happens. Now, in this SO4 2 minus ion, the central atom sulfur has 4 half-filled sp3 hybrid orbitals and 2 unhybridized d orbitals. It is very well clear that these half-filled hybrid orbitals, 4 sp3 hybrid orbitals, leads to the formation of 4 sigma bonds. and unhybridized orbitals leads to the formation of 2 pi bonds. Hence, in sulfate ion, SO4 2- ion, there are a total of 6 bonds. And in these 6 bonds, 4 are sigma bonds which are produced from 4 half-filled sp3 hybrid orbitals and 2 are pi bonds. So, in this structure, it is clear that there are a total of 6 bonds and this is sigma, this is sigma, this is also sigma, this one is the 4th sigma bond. This double bond, this is a pi bond, this is also a pi bond. So, among the total of 6 bonds around the sulfur, you can see that 4 are sigma bonds and other 2 are pi bonds. The sigma bonds are produced from sp3 hybrid orbitals. Now, based on the hybridization and VSEPR theory, the geometry can be predicted. The geometry, you know, it is tetrahedral geometry. This is because of the direct consequence of sp3 hybridization. This is the tetrahedral geometry. Since there is no lone pair, you can say that the geometry as well as shape of sulfate ions are the same and both are tetrahedral. This is the tetrahedral arrangement of sulfate ion. Moreover, we have to say the important point that the sulfate anion also shows some resonating structures. These are the 6 resonating structures associated with the sulfate anion. Now, we are discussing structure of anions with lone pair on central atom, that is nitrite and sulfite ions. That is, we are going to look at 2 important ions, that is nothing but a nitrite ion and a sulfite ion. In the nitrite ion, the central atom nitrogen shows sp2 hybridization. So, the sp2 hybridization scheme can be represented like this. Nitrogen atom in the ground state has an electronic arrangement of 2s2 2p3. This is the arrangement. So, nitrogen atom in this arrangement can be represented by using box-wise representation like this: 2s2 2p3. Since in nitrogen atom there will be no d orbitals, there will be no probable excitation, and in this case nitrogen undergo hybridization, that is nothing but a sp2 hybridization. One s orbital and 2 p orbital undergo hybridization. That hybridization is nothing but sp2 hybridization. One hybridized p orbital is also here. This unhybridized p orbital lead to the formation of a pi bond, and these 2 half-filled hybrid orbital lead to the formation of 2 sigma bond, and this exists as a lone pair. So, in this structure, you can see the presence of this lone pair. This is the lone pair and 2 sigma bonds. This is a sigma bond, this is also a sigma bond, and this half-filled unhybridized p orbital lead to the formation of a pi bond. That is the geometrical arrangement of nitrite ion due to sp2 hybridization. Now, the hybridization is already predicted based on VSEPR theory. The geometry is already predicted. So, this molecule exhibits trigonal planar geometry with one lone pair on the central atom, nitrogen. This is the arrangement. You can clearly see the presence of a lone pair here. And since there is a lone pair on the central atom, you can say that the geometry is different from shape. The shape of the molecule is obtained by ignoring the contribution from the lone pair. So, you can say that this molecule NO2- ion shows a bend shape or V shape, and the shape is similar to that of water molecule. That is why we can say that it is bend or V-shaped molecule. Now, we are discussing the structure of sulfite ion SO3 2- ion. In sulfite ion SO3 2-, the central atom sulfur shows sp3 hybridization. The hybridization scheme clearly determined from the molecular formula, and from the molecular formula we can arrive at the hybridization as sp3. sp3 hybridization leads to the geometry of tetrahedral geometry, and in the central atom sulfur there is the presence of a lone pair, and that lone pair can also be clearly seen in the geometry. So, the exact geometry of the sulfite ion SO3 2- ion is tetrahedral with one position occupied by the lone pair. This is the exact geometry of sulfite ion. Now, we can arrive at the shape. In order to get to the shape, you have to remove the only one lone pair present on the central atom of central atom sulfur. the shape is obtained by excluding the lone pair. On excluding the lone pair, we will get a shape that is nothing but the pyramidal shape. That is, the shape of sulfate ion is pyramidal. The geometry is tetrahedral with one position occupied by lone pair and the shape is pyramidal. That all about the present module. Have a nice learning experience. Thank you.